Okay, so now what? We've got these two models, went to all this trouble, coming up with, somebody did, deriving, understanding these two different models, and they look exactly the same in terms of their ability to describe what's going on. And as I mentioned the last time, they're not the same model, right? The underlying molecular physical assumptions of those models are very distinct, yet they're indistinguishable. So I left you at the end of the last section asking, well, what do you do? Okay. Well, when faced with situations like this in your science, and you will be someday, probably many more times than once, what you have to do is think about, well, what are the predictions of my model? This is one of the things that we think about and worry about in science a lot. Models that make predictions are useful. Models that don't make predictions are useless, right? So are there some predictions from these models that we could go and figure out a way to test a different way? Maybe then we can distinguish, even though mathematically they're both fine and they both work and they both describe the binding data, they're indistinguishable at that level of analysis. But maybe there's some other prediction they make. What could they be? Think about that. One prediction is that in the case of hemoglobin, the KNF, the sequential model, predicts at least 4 intermediate liganded structural states, right? As those binding constants cascade and the strain, the asymmetry slowly works its way through the molecule. The MWC model, by contrast, predicts you only ever see 2 states, T state and the R state. That's all you need. Oh, so they do make a very specific prediction about the structural distribution of the hemoglobin tetramer as you put in the ligand. Oh, okay, well, what if we go and look at that? Okay, well, the guy who started looking at that to begin with, the person who solved it, was a man by the name of Max Perutz, right? Began the study of hemoglobin in 1937 at the Cavendish lab with Lawrence Bragg, John Kendrew, some of the other great famous people who built what we think of now as structural biology, initially around X-ray crystallography. This is the group that did the very first application of X-ray diffraction to large macromolecular as opposed to small organic molecule structure. And Max started working on this problem in 1937. He didn't solve it until 1968. That's 30 years on one problem. Wouldn't it be nice to get that kind of time to work on a good problem? Well, the world has changed. And he did solve it, right? It's one of the great contributions to science and to biochemistry, our understanding of basic biology. And of course, he won the Nobel Prize for this eventually. And one of the striking things about this and work that was done for decades after, this picture's gotten more murky recently, but for decades, when people did crystallographic studies of all different kinds on different hemoglobins, they would only find 2 states. They would find the deoxy state and the oxy state. So that, to a first approximation, sounds an awful lot like MWC, right? Only 2 states. Even better than that, when the people looked in detail, right, which Max was the first to do, at the conformational properties of the deoxy T and oxy R state, virtually all the structural changes they could see were at the level of the tetramer interface, right? The tertiary structure of the individual subunits between the T and the R state is virtually, in the crystal structures, indistinguishable. They can see no significant difference within the error of the ability to pin down where those atoms are. They look the same, right? And all the structural changes they could see happen at the interface between the subunits. Okay. Now that has been interpreted as a strong indication of an MWC-like cooperative transition. Only 2 states, all the structural changes happen at the level of the tertiary structure, at the level of the quaternary structure. And if you know some things about crystallography, how it works, you could punch some holes in that argument. People certainly did. We'll talk about that in class, right? But okay, it is what it is. That's what people saw. Only the deoxy and oxy state The only structural differences really between them are between in the oligomer interface. Specifically, those changes are between the so-called alpha 1 beta 2 and alpha 2 beta 1 interface. Now remember, the heterodimer is made by an alpha 1 beta 1, right? But there's another interface, right, between those two heterodimers. When they come together to form the tetramer, there's another interface between the other subunits that aren't in a formal heterodimer together, but they still touch each other. And almost all the changes, not all, but most of the changes are in that interface. All right, so let's take a look then about the way in which Max, looking at the structure with the level of atomic detail he had, how he and colleagues interpreted the structural changes that lead to oxygen binding and cooperativity, and how they thought about how it works. And sort of if you look back through some of the papers and the reviews of this body of work, you'll see Max seems to the explanations kind of oscillate back and forth between, yes, it's very much MWC-like, and no, it really isn't. So I'm not sure. A lot of people have really interpreted the structural biology, at least up to a certain point, as being consistent with an MWC-like model. But let's take a look, right? Okay, so we talked about the big picture structures, right? So before we dive into the detail, let's think a little bit about the energetics of the situation. So, let me back up again. Let's take a look at that interface again. Forgot I wanted to show you this to you first. So here again, that I started drawing out. Here's that alpha 1, beta 1, alpha 2, beta 2. There's the two heterodimers. There's the interface. They come together. You rotate this guy sort of 90 degrees. You can see that alpha 1, beta 2, alpha 2, beta 1 interface. It's back over here, right? And what turns out to be the case is right along this interface, right? Because here's alpha 1, here's beta 2. There's that interface. When the molecule, the heterodimer, goes from, the tetramer goes from deoxy to oxy, what essentially ends up happening is the two heterodimers kind of rotate about 15 degrees and translate into each other just a bit. It's like a screw motion as they sort of like rotate and squeeze down, right? And that's more or less the motion that dominates structurally what's visible in the crystal structure of going from deoxy to oxyhemoglobin, right? Like I said, the tertiary structure of the individual subunits doesn't seem to change significantly. Okay, so what's the big idea, right? The idea here, energetically, is that in the absence of the ligand, the T state is more stable than the R state, right? And as a result of something we're gonna look at in a minute, when Max got a detailed look, the idea is that in the T state, the molecule is constrained. There are a set of structural interactions within the heterodimer that keep the affinity low, right? And that set of constraints can be thought of as an internal structural strain, right? And so this term T literally came from the idea of this state being tensed, right? In the sense of a stored spring, a spring that had been stretched that was storing energy, right? And that's somewhat unstable, right? You got to have something that's holding that thing, that potential energy cocked in a way. But the idea here is that the alternate conformation of the heterodimer, in the absence of some other stabilizing interactions, hint, hint, binding of oxygen, is even more unstable, right? So the T state, whatever those interactions are that keep it tensed, is more stable than the R state in the absence of a ligand, right? But there's still this sort of like stored energy in the structure of this molecule that can be used to enhance binding. And that's the idea, is that once oxygen binds, the relative stabilities flip, right? And in the presence of lots of oxygen, the R state now is significantly more stable than the T state. And essentially that energy that was holding the T state tensed is released into increasing the affinity of oxygen for hemoglobin by changing the structure of the molecule. And so that's where R gets its name. This is also known as the relaxed state. The idea that that tension in the T state has been released and used to increase the affinity by changing the structure of the molecule. Okay, so that's the big picture idea. How does this work in detail? All right, so for that, we need to drill down a little bit and remember how oxygen binding works. Remember, we've got this tetraperol, this protoporphyrin heme, right, with iron right in the middle. There are those four ligation sites of those nitrogens from the tetraperol. We have on one side, one octahedral position, that so-called proximal histidine, coordinating one of the above plane interactions. And on the other side, we have the oxygen binding pocket, but it's not sitting there by itself. There's a little pocket here in between the so-called distal histidine, which is attached to helix E, right? And that little pocket it's just perfectly positioned to sort of snuggle the oxygen in between that histidine nitrogen and the iron in the middle of the heme. Okay, so where does all this sort of tension, stored spring energy comes from? The secret to how this works is substantially played by the so-called proximal histidine, its connection to the heme iron, and its, of course, being incorporated into the polypeptide, its connection, covalent connection to the so-called F helix, right? And here's the idea. In the absence of oxygen, like I said, the histidine, the proximal histidine is connected to the iron, which is connected to the F helix, which is connected to the rest of the molecule. Leg bone's connected to the ankle bone, right? And what happens is, by virtue of packing interactions both around the heme itself, as well as a set of interactions we're going to look back in a minute. But if you remember back that alpha 1 beta 2 and the beta 2 alpha 2 interface, that interface at the heterotetramer that changes, there's a set of interactions there that pull back on the structure, that pull back on the F helix, pull back then on the proximal histidine, which is liganded to the iron, which now pulls the iron, tries to pull the iron up out of the plane of the heme. Now, the heme with the iron, it doesn't want to be domed. It wants to be flat, right? The electronic structure of these nitrogens that are coordinating that iron, those orbitals don't want to be cocked up at some weird angle, and you're pulling on the rest of these bonds. These things are conjugated. They got pi bonding. They want to be freaking flat, right? So to do that, you're basically putting a destabilizing energy into the conformation of the heme and the iron position, doming the heme up. That's energetically unfavorable. The thing really wants to flatten out, but that's okay, because you've got a lot of energy in the positioning of this helix and how you staple it in place at that interface to keep this thing pulled back. And that then is your cocked spring, right? Okay, so let's get a look at those interactions, right? So this is the set of interactions at the alpha 1, beta 2, alpha 1. There's a little other places, but this is a big part of it. Basically, there are a set of salt bridging interactions and a set of hydrogen bonds, right, that are critical for stabilizing the T state of hemoglobin, the deoxy state of hemoglobin, right? And they're essential because this is what's paying the energetic price of pulling the F helix back and pulling that proximal histidine part of the way back and doming up the heme, right? It's all stabilized by this set of salt bridges and hydrogen bonding interactions, as well as some other packing interactions around the heme, but this is a big part of it. In addition, these hydrogen bonds, some of these key hydrogen bonds are a major explanation as they change for the Bohr effect. Interestingly enough, you should think about that. Okay, that's great. So now what happens when oxygen binds? All right, so we bring oxygen in. Here it comes in, binds in that nice little pocket between the distal histidine and the heme on the last remaining octahedral coordination position. That now provides this significant driving force. Right? The iron really wants to interact with the oxygen, but it can't interact with the oxygen if it's domed up, because the oxygen's held partly in place by that histidine on the other side. So to get to it, to get the bonding orbitals optimized well, and to collect the significant enthalpy that's associated with forming that coordination complex with the oxygen, the iron has to move, has to flatten. All right, and remember, the heme doesn't like being like this anyway. I keep anthropomorphizing. It's not energetically favorable for the heme to be domed, right? There's already a driving force for intrinsically for the heme to flatten out, which would reposition the iron, get it closer to the oxygen. That's a good stabilizing thing. But to do that, you got to move the proximal histidine. And to move the proximal histidine, you got to move the F helix. And to move the F helix, you got to move what it's attached to, what it's connected to. And to do that, you have to basically rupture that alpha 2, beta 1, beta 2, alpha 1 interface. Those salt bridges and those hydrogen bonds, you more or less have to disrupt those. You have to pop that interface. And the interface between those subunits is sort of designed like a toggle. It's kind of got two positions. One where those positions are engaged and one where they're disrupted, and the packing interactions, that interface shift, right? Sort of sideways, right? This is part of what that rotation and translation gets you, is the breaking of all those interactions that stabilize the T state and resetting to a set of interactions that are compatible with the R state. So to get this to work, then binding of the oxygen is coupled to a structural change through the F helix back to the dimer interface. And because these interfaces are connecting multiple subunits, the idea is they can't go one at a time, right? Because the set of packing interactions between these guys are all connected to each other. They're linked. In the same way that all the interactions that hold a globular protein together are linked, these guys are linked to each other. You can't move one without moving the others. So to rearrange this interface, you got to pop them both, or you have to shift the whole quaternary structure of the molecule from T to R. All right, that's the idea. So to give you a sense of how this works, if you take the two structures, the oxy and deoxy form, and you do a little sort of computational magic, and you just do a simple extrapolation between the two, this is kind of what it would look like. So here's an oxygen molecule. Here's our heme. This is one subunit. I don't remember if this is alpha or beta. Its buddy, its pair subunit in the alpha beta heterodimer is this guy back here, right? And here's the interface going across back here. You can't see it. Here's the other beta, the other alpha back here, right? There's the oxygen. There's the heme. There's the proximal histidine, and there's its connection right there in salmon is the F helix. And look what happens when oxygen binds. You let go, right? And you can see that the proximal histidine, right, when the oxygen dissociates, slides back because those interactions now are more stable. That pulls the F helix back. The F helix attached to the rest of the alpha subunit, which is attached to this interface. And all these guys are connected together in the heterodimer. So the whole thing acts like a structural toggle. Shifting, right? And remember, you're going to pop one of these guys. You're going to move one of these guys and change this interface. The idea is that you can't just do one F helix. You got to do all of them, right? You got to move all of those F helices, because all those interfaces, the alpha and beta subunits, they're all connected back to F helices that are connected to histidines that are connected to irons. So you pull one back, right? Pull one in to bind an oxygen. You're going to pull in that interface. That's going to release the other guys. So they all kind of go as a unit, right? That's the basic idea. Okay. So the question then remains, is that a convincing argument based on everything we talked about for NWC? Could it be interpreted as K and F like? Some people, and even Max himself, I think probably saw this as something, a third option, sort of maybe in between these guys, not really clear. A lot of people over the years have argued that the structural biology comes down pretty heavily on the side of an MWC-like model, right? And I think that's where the argument rested for a good long time. But there were some dissenting voices, right? And we're going to take a look at some of the data that suggests it's probably not that simple on Monday.